Hello, and welcome to this introduction to the Military Standard 1553 Communications Bus. There are dozens of communication buses in the market, all of which are meant to do the same job: gather data from one place and bring it to another. We will explain why there are different types of buses, and why some are more appropriate than others for particular applications. We will then focus on Mil Standard 1553 and show how it was designed specifically for real-time military avionics applications. An avionics bus is a means for moving information from one part of an airplane to another. For example, getting information from a GPS to the pilot's display screen, or from a button next to the pilot to the landing wheel assembly. When we say real-time, we mean within a defined time constraint. This constraint may be different for each type of information. The acceptable time between pushing the landing gear button and having the landing gear come down may be longer than the time between hitting the ejector seat button and ejecting. By looking at several different buses currently in use, it is possible to gain an appreciation for some of the trade-offs and design decisions involved in each design. ARINC 429 was the first generation of digital communications on civilian aircraft. Mil Standard 1553 is the most widely used bus in military aircraft. AFDX is the newest generation bus being designed onto both Airbus and Boeing aircraft. It's worthwhile to learn some of the language of avionics buses before diving into the details of the specifications. Sometimes different buses use different terms to describe the same thing. An avionics bus is a means for communicating between different parts of an airplane. A remote terminal or end system is a part of an airplane that needs to send or receive information to or from another part of the airplane. We will give examples of these soon. A source is a remote terminal with data to transmit. A sink is a remote terminal that needs to receive data. Dual redundancy is the use of backup systems so that if part of the communication system fails, the data will get through via the backup route. Now, Orville and Wilbur didn't need an avionics bus. If they wanted to know how high they were, they could either look at a gauge that both measured and displayed altitude, or they could look over the side of the plane. They might have had a similar gauge for speed, or they could just look at their watch as they flew over landmarks. For direction, they had a compass. None of these devices needed to communicate with any of the others. As aircraft got more sophisticated and safer, more devices were added that needed to share information. The altitude in a modern aircraft is needed not only by the pilot, but by the autopilot and flight recorder as well. An engine may communicate with all those devices, plus send data to a maintenance log. In the 1980s, ARINC 429 was introduced, bringing together a number of similar specifications that had been introduced piecemeal over the previous few years. ARINC 429 connected a wire directly from any device needing to send data to any device needing to receive that data. As long as the number of devices were fairly small and the distance of the devices from each other was fairly short, this was a simple and elegant solution. Let's look at a military application. A fighter plane is armed with multiple missiles. The pilot needs to know the status of each missile. He needs to be able to check if they are in working order, to see how many are available, and to fire them if necessary. A flight recorder is used to note all activity for later review. So each missile needs to connect to each of the devices used by the pilot to control them. Let's see how this would look if we used a bus like ARINC 429 to make these connections. Even with our fairly simple model, the wires are beginning to resemble a bowl of spaghetti. As we add missiles and add devices, it is easy to see that the wiring would get out of hand very quickly. Another model for communications is therefore necessary. The model introduced by MIL Standard 5053 is essential wire shown as a double red line in the diagram that each device is attached to once. The difficulty with replacing all the individual wires of ARINC 429 with the single wired 1553 is that if more than one device decides to transmit at the same time, the data will get jumbled. Even if only one device is transmitting, how does anyone know who's it transmitting to? It would be unfortunate if the trigger button always caused all 4 missiles to fire. MIL Standard 1553 therefore introduced the notion of a bus controller. The bus controller, or BC's, job is to coordinate between the various devices so everyone knows whose turn it is to talk and whose turn it is to listen. The advantages of MIL Standard 1553 relative to ARINC 429 for aircraft with large number of devices with complex interactions all stem from a much smaller number of wires and connections needed to connect the devices to the bus. Fewer wires means less weight, which is a critical issue in aircraft design. In addition, fewer connections means fewer places that might break, which relates directly to the mean time between failures, or MTBF, of the aircraft. Finally, the ability to add or exchange devices by changing only a single connection is a tremendous maintenance advantage. We briefly noted the role of the bus controller. Let's discuss it in a little more detail. The MIL Standard 1553 bus controller decides the order of messages that will be sent over the bus. In ARINC 429, every device could send data at will. In 1553, the BC tells each device when to send and when to receive. In addition to controlling the order of the data, the bus controller also sees all the data. When the pilot asks for status of a missile, that request goes to the bus controller. The bus controller will then retransmit the request to the appropriate missile. By being in the middle of all these transactions, the bus controller can keep track of the success or failure of each message. If the bus controller detects communications failures, it can take steps to correct them or inform the pilot that some devices are offline. Of course, there is a price to be paid for the low weight, low maintenance advantages of MIL Standard 1553. By moving all communications onto a single wire, we have a situation in which, if that single wire is damaged in flight, all critical systems will fail at once. Now, this is a bad thing. That is why all 1553 buses are dual redundant. They are designed with sufficient backups, including a backup BC, so that no single point of failure can cause a catastrophic event. The need to share a single bus also has an efficiency cost. When a device has something to transmit, it must wait for the bus controller to give it permission, regardless of how critical its data may be. There are several mechanisms in place to deal with this issue, including the higher speed of 1553 relative to 429, and the ability of the bus controller to prioritize messages through the use of minor frames, which we'll describe in a later session. Now let's look at AFDX. AFDX also allows each device on the aircraft to have a single connection to the bus. It handles collisions by connecting each device to a switch. The switch then forwards messages to the appropriate device, which is connected to a different port on the switch. If multiple messages are received by the switch simultaneously, the switch holds them in its own memory and sends them out one at a time. A system architect instructs each device on the switch how often it is permitted to transmit messages so that the switch never becomes overloaded beyond its capacity. Now, to review, for a simple configuration involving few devices, wiring directly from each transmitter to each receiver is simple and inexpensive. When the configuration gets more complex, a central bus shared by all devices is much more efficient. The central bus simplifies wiring and connecting new devices, but introduces issues of control and prioritization of messages, which will generally be dealt with by software. This concludes the first part of our Mill Standard 1553 course. Our next session will go into more detail of the mechanisms used by 1553 to deal with these control and prioritization issues. If you have any questions or comments, you may find our contact information on our website at www.mill-1553.com. Thank you.